Okay, so today we are going to be having a discussion on atomic orbitals and atomic numbers in general. Or I guess quantum numbers. So, first, we are examining an atom with electrons. Um, and so, let's kind of start out with some of the basic definitions we'll be using. So, the first definition is orbital, and an orbital is just a three-dimensional region around the nucleus that indicates the probable location of some electron. So it's just a area around the nucleus. So if we have something like an atom, we have a nucleus here. An example of an orbital would be a sphere. So this would come out of the um, paper, and it would basically just designate the most probable location for an electron. So, with that being said, we have a notion of quantum numbers. They specify the properties of an atomic orbital and the properties of the electrons in those orbitals. So, there are four quantum numbers. The first one is the principal quantum number, which we represent with an n. N can be anything that is 1 or greater, so 1, 2, and onward. And it gives us more or less the energy level occupied by the electrons. And higher values of n are associated with farther distances, farther average distances from the nucleus. So if I have two orbitals that are both spherical, if I have my nucleus here, and then I have one orbital that's out here, and one out here, I don't need to know that this is n equals 1, but I know that whatever n this is going to be, if this is n1 and this is n2, I do know that n2 is greater than n1, just because the n2 is laying farther out. So, with that being said, we have a notion of angular momentum quantum numbers, and it gives us the shape of our orbital. So, what are the possible values for L? L is going to be less than or equal to, I guess it's going to be greater than or equal to 0, less than or equal to n minus 1. So we would have like 0, 1, all the way up to whatever value you have for your n, subtract 1. So, for example, we typically associate, or the L gives us the angular momentum, and really the thing L gives us that is a reasonable thing to like wrap your head around is the shape. And so these are spherical, and what we call these, or what L values associated with these spherical orbitals would be L equals 0. So if you have a spherical orbital, that would be L equals 0. So what are some other shapes? So let's see here. We have the L equals 0 case, which gives us a sphere, and we call that the s orbital. So let's start fresh. So we have L equals 0, and that's going to be, if we draw out our three axes, let's see, it would be a sphere that would go, completely around that center point, and this would be our s orbital. I wonder, your book might talk about what S is for. I would guess, if I'm not wrong, I feel like S might stand for sharp. If I had to take a guess, because I know most of these abbreviated letters come from spectroscopy, where they would examine peaks, and I think some of these are from how their shapes look on a spectroscopy chart. So Not that you need to know that, but there is a reason for why it's S. Um, like I think there's one we'll talk about eventually called D, and I think that means like defined or definite. And P, if I had to guess again, would be something maybe like principle. Not that that matters. Just it's good to know that we didn't just randomly pick these values. It has something to do with spectroscopy. So with that being said, we have the next case, L equals 1. And so what this will look like is a kind of a dumbbell shape or an infinity symbol. And remember, this is not only, so this would be on like the x-axis, but also remember this is coming out of the board. So it would be, the shape would be what you'd get if you took and rotated it around the x-axis and basically made these kind of balloon shape. These two circles made it kind of balloon shape. So in the end of the day, you get something that looks like if you took maybe two teardrops and stuck them together end to end. That would be what this shape is. And so we call this the p orbital. So these are the two big ones. These are the ones that I'll probably ask you to actually remember because they're the ones that we see the most often. But let's go a little bit farther. I think the last one that I really think is important or has some importance to know is L equals 2, and that's going to be a double dumbbell. And it is going to be called the d orbital. So these are the different shapes we have. So let's think a little bit about this. If we take our, I think our L equals 2 case is a little too complicated, and our L equals 1 or L equals 0 case is a little too trivial. So if we just look at this L equals 1 case, we have this orbital right here, and it's on the x-axis. So if you think about it, really, it doesn't have to be on the x-axis. So we could have one where we have, this would be y, x. So we'd have one that's sitting on the x-axis. We could have one that is sitting on our y-axis. And then lastly, we can have one that's sitting on the z-axis. Let me make sure I get my axes right. So we would have y here, x, and then just a y. I think this would be my z. So or my positive z-axis. So we could have this as z and then y, and we could have another dumbbell shape here doing this. This would be our p orbital about the z-axis, so that's sitting on the z-axis. So there's 3 different possible orbitals that we can have. One on the x-axis, one on the y-axis, and one on the z-axis. And something that we'll see is there is a way to say the number of possible orbitals. I think really getting the one for D, it's just a little bit too involved to talk about. Especially if you look in your books on page 103, the section that talks about the dz squared, that is kind of a nightmare to wrap your head around, and like why is it doing exactly what it's doing. So I don't think we're going to go into the d's, but really as far as these orbitals, the p orbital has an L of 1, and we see there's 3 different ways we can write it out. The s orbital has an L of 0, and how many ways can we write this out? Well, there's no way that we can reorient this. It's always going to be a sphere, so there's only one way to write it, or only one type of orbital that has an s, there's only one s orbital where there will be 3 p orbitals. And the reason for that is we can take our p orbitals and put it on the different axes to get different possible orbitals. And so we can talk about the p sub x orbital, the p sub y orbital, and the p sub z orbital. So the s orbital doesn't have where that's possible, and the d orbital we allow for things like the d comma s d comma x z orbital, d comma x y, d comma y z. It's really based off of the allowed orientations. We aren't going to get too much into that, but I think the important thing to note is that orientation allows us to specify more further what orbital we're dealing with. And so we have this n that gives us our principal quantum number. So, and it's just 1 or greater. We have L that is greater than or equal to 0 and less than or equal to n minus 1. And then we have our orientation value, the value that gives our orientation, and we're going to call that m or m sub L. And basically that value will be at its smallest negative L and at its largest L. And so something we see is when L is 0, what are the possible values for m sub L? Well, just 0. And so that's why we only have one possible orbital, or I guess suborbital, for our m sub L. We only have one orientation for the case where L equals 0. So that m sub L is telling us that. It's saying there's only one way we can orient a L of 0. And that will be, about the origin. We'll have our sphere located about the origin, or at the center. When L equals 1, what are the possible values for m sub L? Well, that would be negative 1, 0, and 1. And so this gives us the different ways we can, or the number of ways we can orient our orbitals when L equals 1, our different dumbbell orientations. And so this m sub L just says what is the orientation of our orbital. Are we dealing with an orbital that is on the x-axis, the y-axis, the z-axis? What is the orientation? So if we have an n and we have an L and we have an m sub L, we have completely defined what orbital we're dealing with. The last value, and let me make 100% sure, dealing with this, the last number is the spin quantum number. It only has two possible values, and so those values are going to be plus or minus 1/2. And basically what this does is inside of every orbital, so inside of every m sub L, let me take a quick look to make 100% sure. So inside of every single orbital, we can fit 2 electrons. So inside of p sub x, we can fit 2 electrons. Inside of p sub y, we can fit 2 electrons. Inside of every one of our orbitals, we can fit 2 electrons. And this m sub s being plus or minus 1/2 is really our way of showing that. If we have an n, L, and m sub L, we can only have 2 different electrons because we need to have each electron with its own unique set of 4 values. If you have 2 electrons with the same 4 values, then they're really the same electron. So this m sub s, there's a lot of other reasons for why it's plus or minus 1/2, but that's really the important thing for us. It has 2 different values, and the reason is it's just telling you you can fit 2 electrons inside of a orbital. So with that being said, let's see if we, let me get rid of this. So let me see really quick if I can find the study sheet we got yesterday, or Friday I guess. Let me see if I can bring that up, just so I can talk about it a little. One second. It might be helpful to work through some of the problems that we're getting people yesterday. Or not yesterday, again, Friday. So let's work through a few of these problems together, and I might even just hand this out again in class tomorrow, just so that we can all kind of work through it in class. But anyways, state the four quantum numbers and the possible values they may have, and so that one would just be n, l, m sub l, and m sub s. N equals 1, 2, and onward. L is going to be between 0 and n minus 1. M sub l is going to be between negative L and L. And m sub s is plus or minus 1/2. So that would be our number 1 right off the bat. So let's see here. Now they want us to name the orbitals described by the following quantum numbers. And so we have n equals 3, L equals 0. Okay, let me take a quick look to make sure this is something that we have covered 100%. Let's see. So I think this might kind of touch a little bit outside of what we've talked about. I'm not 100% sure. Actually, I think I'm not quite getting 100% what it's asking. I'm having a bit of just trying to read it, so I apologize because it must have been a little confusing. But if I'm reading it right, I think we probably have covered it. It's just asking it a little weird. So all it's saying is basically we take that n, and since n is 3, we can say 3, and we have L equals 0. So we know that since our L equals 0, we know this is the s orbital. So this would be the 3s orbital. I don't think our books get into it in the same area that it gets into the other stuff. It doesn't look like it does. But really, we can talk about our different orbitals by the following. We can basically just put our n and then the letter representation of our L. So something like 3 and S, this would be the let's see here, the circle with, I guess, the third smallest radius. So, 3S would be like you'd have your first radius, your first circle, second, oh wow, that was a terrible circle. First circle, your second circle, and then your third. This would be your 3S. And the 3 tells you that it's the third smallest sphere, and the S tells you that it's a sphere. So really the 3 tells you it's whatever shape, it's the third farthest away from, or the third closest to the center, and the S gives you the shape. So hopefully that makes sense. Basically all it is saying that if you give me an N and an L, I can tell you the orbital, and basically what you would just have is N and then the letter representation of your L. So let's kind of just work through those, because I think it makes more sense if we just work through some examples. So if I have N equals 3, L equals 0, what would I have? 3S, because for L equals 0, my S is 0. Or my apologies. For L equals 0, I know I'm dealing with an S orbital, and then my energy level is 3, so I'd have 3S. Then if we have N equals 3, L equals 1, I would have 3 from this N, but now L equals 1, so instead of S, I'd have P. So that's pretty straightforward. Now we have N equals 3, L equals 2. And so let's see, this one would just be 3D. Okay. I gotta admit, the thing that kind of is throwing me a little bit confused is D, because D says n equals 5 and lambda equals 0. I don't think that should be a lambda. I think that should just be an L. I don't know why they decided to invoke Greek letters here, but I think that's just an L. I think they made a mistake. So for this example, we'll just assume they did, and we'd get 5s, which isn't that nasty. So let's see. Question 3 has us just work the other way. So if you have one S, they ask for the N and L values, and so N would be 1, L would be 0. I'm going to skip a few. 2p, N equals 2, P equals 1, and 5f, N equals, that'd be 5, and, my apologies, didn't mean to put that P, the L equals 1, and L would be 0, 1, 2, 3. So, yes, So, this would be how to approach 3. Basically, it's very straightforward. It's just really, if you know that L equals 1, or if L equals 0, you get S. If L equals 1, you get P. If L equals 2, you get D. And if L equals 3, you get F. If you know those, then you can really easily get these between these, because all you do is you say, to get from the quantum numbers to orbitals, you're given n equals some value. So I'll just leave it as n. So if you're given an n and you're given an L, you would just write n and then whatever the letter version of L. So like the I guess not the letter version, but the like the S, P, D, F version of L. So n is 3, L is 2, would be 3D. Hopefully that makes sense. If you have any questions on that, just let me know. Okay, so with that being said, they want us to circle all the following orbital destinations that are theoretically possible. And so before we do that, let's kind of think about what makes a orbital destination theoretically impossible. And so these orbitals only have, let's see, they only have values of n and L. And so we know that if n is some number, so let's just kind of keep it generic and say that if we have a defined n, and so we know our L will be between 0 and n minus 1. So really what we do is we start out, we look at the value of an orbital, so 7s, and what does this tell us? It tells us n equals 7 and L equals 0. Well, L is greater than or equal to 0, and it's also less than or equal to negative 6. So both of those quantum numbers are fine. So 7s gets the pass. 1p, and so n equals 1, L equals 1. So that's not looking very good, because we know that L has to be greater than equal to 0, less than equal to n minus 1, so L has to be 0. In this case it's not. That's not good for that. 1p, so that's out. And really, that's how you would be approaching the rest of these problems. The only thing that they did that I think is a little bit you know, a little bit scary is they threw this G and I. They didn't give us an H, but so I'm not going to require you to know anything beyond. I know I'm going to probably ask you to know S, P. I might ask that you know D. That's not a horrid number of things to know. Just knowing that L of 0 corresponds to S, L of equals 1 corresponds to P, L of 2 corresponds to D. But the thing is past that, the chemists kind of decided to start making sense. And so it's kind of unfortunate that the first three values are the ones that make absolutely no sense, like how do you go from S to P and then P to D. But as soon as you get past that, you get L3 goes to, I guess this one doesn't make a ton of sense. It goes to F. But anything past this, L of 4 goes to A, B, C, D, E, F, G. There we go. That wasn't as bad to keep track of. L equals 5 goes to A, B, C, D, E, F, G, H. That's some good chemistry we're doing right there. And we can just keep going, really. If we want to know what L of like, 18 is, we'd probably get into some weird stuff if we went much past that, because I don't know what you would do after you hit Z, but, we're not going to go that far. I think it's just kind of helpful maybe to at least have seen this. I think I will probably ask you to know these. Definitely these. D will be something that I'll probably go a little bit away from, but I would at least have seen this. I'm actually going to tell you that you need to know it, and so you can be pleasantly surprised if it's not on the test. But I'm not sure yet if I want to throw any questions for D on the test, but probably good to study it just in case. Okay, with that being said, let's hit this next problem. Without referring to a text, periodic table, or handout, deduce the maximum number of electrons that can occupy an s orbital. So let's see if we have a s orbital. We have, what is our n? We don't need to know our n, so don't worry about that. What is our L? L equals 0. And really for n, we just pick our favorite n, so n equals 7. L equals 0, m sub L equals, let's see here, that would be 0. And so the only two electrons we have are m sub s equals 1/2. This would be 4 quantum numbers, which defines an electron. And then m sub s equals -1/2. So there are my apologies. There are 2 electrons that can occupy a single s orbital. So the subshell of p orbitals, let me see, because the text didn't seem to talk a ton about our suborbitals. So let's see. Yeah, I'm seeing them kind of dance around using that. Yeah, it looks like our text calls the orbitals like, I'm wanting to make sure that we are correct with this, but they call this an orbital, and it looks like this handout is calling the all 3 possible values for p, all of this. It's calling that an orbital. I'm not going to ask any questions that nitpick, really, and if ever you give one answer when I was asking for the other one, as long as you're right on both, I'll give you full credit for it. But with that being said, we'll just assume this is asking for the subshell of p orbitals, so we'll assume that it's asking for just all p orbitals. So that horridly drawn thing. And so really what I'm assuming this is for some n, so 7. L is, so for our p orbital, L equals 1. Oh, yeah, that's a true statement, but not really helpful. L equals 1. M sub L can be, so here we had 2 electrons because we could make M sub S be 1/2 or negative 1/2. So here, though, we have M sub L can be negative 1, and then we have M sub S will be 1/2 and negative 1/2. So we have so far 2 different electrons. But then we have M sub L equals 0, and so that will give us 2 more electrons for the 1/2, negative 1/2. And then we have M sub L equals 1, and that'll give us 2 more electrons for a 1/2 and negative 1/2. So in all, the p orbital, or the p orbitals, will have the ability to store 6 electrons. Okay, so the subshell of the d orbitals, so I'm going to again just take that to mean all the possible d orbitals. And here really we have n, we can just give it whatever value we want as long as it's large enough. L equals 2, M sub L is going to be between negative 2, or it's going to just be negative 2, negative 1, 0, 1, 2, and really each, so how many different M sub L's will this be? 1, 2, 3, 4, 5. Each of those M sub L's are going to be in orbitals, so we have 5 orbitals. Each orbital can hold 2 electrons, so that means our d orbitals in all will hold 10 electrons. And I think we are fine. We don't need to go into any of the higher ones. So, with that being said, there is a discussion of electron configuration, and this is the arrangement of electrons in an atom that will basically describe what that atom is. So, there are a bunch of rules for how we govern these electron configurations, and the first rule or principle we use is called the Aufbau principle, and it says an electron occupies the lowest energy orbital that can receive it. This is kind of just how a lot of chemistry and physics works. Things like to be in their lowest energy state. If you see something like a boulder sitting atop a hill, you kind of think to yourself, this is a somewhat precarious situation, because the boulder kind of wants to, in a way, roll down to a place where there's less potential. Everything kind of operates like that, where they want to go from high potential to low potential. And so Aufbau's principle is really just saying electrons follow that as well. They want to be in the lowest energy orbital that they can be in. So with that being said, if we have a let's see, I think probably a good idea here to write out the energy diagram. And so a lot of different ways this is written, a lot of confusing things that kind of occur, but we see the lowest energy is going to be our 1s, and we have 1 orbital for that. Then we have our 2s, and we have 1 possible orbital for that. Then we have, let me make sure I'm getting this right, then we have a little bit above that, we have our 2p, and that has 3 possible orbitals, because we have the x-axis, the dumbbell on the x-axis, dumbbell on the y, dumbbell on the z. So each one of these bars really represents a m sub L value, if that makes sense. Each one of these are orbitals, they represent a m sub L, and instead of saying 1/2 or negative 1/2, we would just give a up arrow, half arrow, and down half arrow. This will be positive 1/2 spin, negative 1/2 spin, and so really let me write this energy diagram out, and then we'll kind of get into talking about it some. So we have 3s comes next, then 3p. Let me call this 2p, 3p. And then I think this is where things get a little weird. Yeah, we end up getting a little weird here because we go up and we have 3D would be like here. But the problem is we have right below that we have 4s, and so we actually, if we start filling up these with electrons, we can only put 2 in each section. So we would go fill this, then this, then this, then this, then actually that's not correct. Let me. I want to while my end result was going to be correct, I kind of want to take the slow approach. The only thing that I do think is going to be important to note from the get-go is this 4s will start filling before my 3d starts to fill. There's ways that we can kind of think about this that makes it not as confusing, and I'll kind of mention one of those ways that I kind of like to look at it that simplifies things. Actually, I might as well just say that right off from the get-go. When you look at the periodic table, there's kind of a way to easily work out why that is. So, not that I don't think it's a good idea to bring out the periodic table quite just yet. So right now, I would just ask you to look at this and not need to really memorize where everything falls. Just if I give you something like this, you can put the electrons where they would go. But I think it is important to know that it won't always be where for the higher ends fall higher up, where at least we can run into a situation where the 3s will fall above the 4s depending on what that L value is. So that's a little confusing, but right now that's not what I want you to know. The big thing I want you to know is off-ballast principle, which says that electrons will always occupy the lowest energy state. And so that just means we fill up from bottom to top. And so this would be increasing energy. And so that's the big thing to know for this. The other thing is Pauli's exclusion principle that tells us no 2 electrons in the same atom can have the same set of 4 quantum numbers, which is really, in our diagram, just saying that we can't have 2 up arrows in the same orbital, but it's also saying that you can't have 2 electrons with the same n, L, m sub L, and m sub s. So finally, we have Hund's rule, and Hund's rule is just saying orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron, and all electrons in a singly occupied orbital must have the same spin. Let me see, because I remember being taught, let me see if we talk about it. Doesn't seem like we really get into it. I've always been told to draw up arrows before I draw down arrows, and there's a reason for that, but it doesn't look like they are getting into it. Let's see. I don't see any direct statements, but I would always just draw your up arrows first, just to be safe. So, with that being said, if I give you a energy diagram, if I for example draw out 1s, 2s, my bad, 2p, and really this would be 2px, 2py, 2pz, and then 3s, and just went on. And I kind of told you that the energy was following this general trend, so you wouldn't have to worry about, on your own organizing these. If I were to ask you to give me the electron configuration of, let's see here, sodium, or actually no, lithium. Let's go lithium. And so in order to find this, all you would do is you would say, well, I know lithium has 3 electrons, and so you would take your first orbital, and you'd say that I have to start at my lowest energy orbital, put 1 electron in, then I can put my other electron in. Go to my second orbital, put 1 electron in, and I filled out all 3 of my electrons, so I am done. If we wanted to do a little bit more interesting case, let's say oxygen. Here we would have, let me make 100% sure, we have 8 electrons. So, 8, wow, that looks horrible. 8 electrons. And so how do we draw that out? We would still have this, the first 2 would fill out like this, next one would fill out up, then down. And now here's the important thing, we would use Hund's rule, and so we would not fill out a single orbital completely until we filled out all of them. And so we have 1, 2, 3, 4, 5, 6, 7, 8. This would be the electron configuration of oxygen. So, let's see. Finally, I'm going to make 100% sure. Does look like they go a little bit farther. Okay, we're also going to talk about noble gas notation. Let's see. So, if we do this, if we have something like, all of this, there has to be an easier way to write this out. So there is, and the way that we write this out is we just say, instead of drawing this as 1s with the up and down electrons, we say 1s, 2. And making sure my subscript is right, my superscript is right. So 1s2, and so that's what this becomes. Then this becomes 2s2. This 2 here is just saying the number of electrons in the orbital. This 1s is just talking about this. So really, this 1s goes here, and then simply the number of electrons in that orbital will go here. So this 2s orbital is full, so we call it 2s2. And then lastly, we have 2p, and then we will give it its the number of electrons, so 4. Hopefully that makes sense. And you should be able to take and convert between the 2 of them, so you should be able to convert between those. And really the important thing is knowing how to do the second one of those. So if I want the electron configuration of chlorine, so how many electrons does chlorine have? It has 17. I know that, and I'll probably give you the order that we have 1s, then 2s, 2p, 3s, 3p, let's see, 1s, 2s, 3s, 3p. I might not actually give you the order because there's an important little trick that you can learn that I'm going to kind of go into. I might as well actually just go into it right now. Let me see if it's something I want to make sure I don't end up accidentally teaching this 2 times in a row. So let's see here. Yeah, so I think if we take a look at the periodic table, so if you take a look, you have kind of this section here goes over, down, over, up. Then we have something that looks like this. And so if you look at this periodic table, what you see is this first column is going to be your 1s1 and 1s2. Then you'll drop down, and this right here is called your S block. Everything inside of these two columns are going to have the highest electron value will be an S. So this will be 2s2 right here. This will be 2s1 will be the farthest value. This will be 2s2. This will be 3s1, 3s2, and what we'll see is as we keep going down, we'll go to 4s, 5s, and so really, if you look at it, you have your s's are in this block. This really should go here for this. That's kind of a weird. Helium sits in a weird place where you can either put it here and it makes sense for some things but doesn't make sense for others, or you can put it here for some and it'll make sense for some things and not makes much sense for other things. In this case, we'll throw the helium over to here. So this section will be our S block, and basically every atom over on this side will have its highest electron, its most energetic electron will be in the S orbital. Then we call this over here the P block, and basically it has the property that its most energetic electrons, or all of their most energetic electrons, 1, 2, 3, 4, 5, 6, will be in the P orbital, one of the P orbitals, and finally, I think the only other really, really important one that we go into is going to be this D block. And these D blocks will have their most energetic in the, and I'm not going to have the right number, but the D block will have its highest electron, most energetic electron in the D orbital. So the important thing, and this is definitely a little bit of extra kind of having to think through things, but if we call this our first row, this is our second row, third row, fourth row, fifth row, sixth and seventh row. I'm only going to ask you to know this up to like the D4, so and we'll get into exactly what I mean by that. But basically, when you go to write out the energy states, you will start here. This will be 1s1. Then you'll go to the next one, 1s2. Then you'll go to the next one, so back to this, you'd have 1s2 because you have the electrons from the first two, and then this third electron will be 2s1. Then you'll go to the next one, so we have one more electron, and so 2s2. Then you'll go over here, and so now you have 2p1. Then you go to the next, 2p2, go to the next, 2p3, all the way over. You get the neon. That'll be 2p6. That'll be right there. And so now we drop down a row. We go 3s1, s2. We go across. We hit that, so we're at the 3p. We go all the way through, get to p6. Here's where the weird thing happens and how to kind of see and take into account what's going on. So we have this 4s2. Now we go over 1, we hit the D block. And the only thing you need to remember is if you follow this procedure, when you get to the D, you just subtract 1 from it. And so you'll start at 3d1 instead of 4d1. If you just start here, and this will be your S1, S2, or 2s, 3s, 4s. This will be your 2p, 3p, 4p.
As long as you kind of go it like you'd read a book, where the if we look at helium as if it were here, everything on this side are going to be less than, are going to have less energy than the things beneath it, and will also have less energy compared to the things to the right on of it. Really, all you have to do is kind of go at it like you'd be reading a book. So if you wanted to know the electron configuration of something like, let's see, manganese. Let me actually see if I can quickly. Let me pull up a periodic table so you don't have to deal with what I'm drawing for you guys. So let's see. Bam. Okay. So let me. Might have just messed everything up. We'll see what happens. Let me make sure my. I'm gonna make it a little bit thicker than that. Might honestly be fine if I make it full. That seems good. Okay, so if I want to know the electron configuration of, let's see, manganese. So how would I find this electron configuration? I start out at hydrogen, and I say I have 1s, and really I know I'm going to hit hydrogen, then helium, so I'm going to have that filled. Then I go 2s because I go back down, down, go to the left again, and so I start lithium, 2s, but then I'll count lithium and beryllium, so I'll have 2s2. I just go to the right, 3, or my apologies, 2p6 because that's going to be entirely filled out. We hit sodium, 3s, and then since we have both sodium and magnesium will be covered by this, we have 3s2. We keep going, we would go 3p, and then we have all of these would be full, and so we would have 6, and then we circle back down to 4s, so we have 4s2, and finally we go to our D block, and remember the only thing with the D is you remove 1 from it, and so instead of 4D we write it as 3D, and so we would have 3D, 1, 2, 3, 4, 5. So 3D5. Hopefully that makes sense. It's definitely a lot to kind of take in, but the important thing is if you think about it, you have so for manganese, we have 25 electrons, and we need to put them starting at the least energetic location and going up to the most. And basically, if we start at the top left-hand side of our periodic table, and we just count off each element as a electron that we can store there, and we record it as its location. So this is your S block, so everything in this column will be NS1, where N is just whatever the row it's on. This will be the most energetic electrons, so you see here this is your 3D5. That is referring to the most energetic electron. In this block, you will have your most energetic will be N times S1. In this column, it will be NS2. So this is your S block, this is your P block, and so you would have the same thing, except now you have NP1 would be this column, then 2, 3, 4, 5, and 6. The only thing really to think about is this row, the D here, and for any of the D's, you'll have n minus 1 D, and then whatever, so this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So, let me see, 1, 2. Oh, my bad, 10, this 10th, so there would be 10 possible values for this D, so 1 through 10. Okay, so hopefully that made sense. This is definitely a weirder section. I think the biggest thing that I would ask you to be able to do is be able to give me the electron configurations of all elements up to xenon. So if you can do that, you'll be golden. What I think I'm going to do really quick is there's got to be a better way to do this. There has to be a better way to do this because it just stopped being able to go back farther. Wanting to just pull back down new periodic table. Get rid of that one. Good. So if we were to solve through for xenon, let's kind of take a slow approach for getting the electron configuration for xenon. Because if you can do it for xenon, you can do it for any of the other ones that I'd like you to do. And so, how many electrons does xenon have? 54. So, number electrons equals 54. And so we need to put those electrons in the right spot. And so I think the first thing to do, we can even write this in the kind of the long-handed approach where we just draw out the orbitals. And so I think this is called orbital notation, where we actually draw out the individual orbitals. And how we would go about doing that is we would have our 1s, which is going to be referring to the orbitals that are hydrogen and are helium have their most energetic electrons in. Then we would have 2s, which are going to be the electrons from our lithium and beryllium. Then 2p, and this would be 2px, 2py, 2pz, z, and that would be referring to this block. I can already tell that I'm not going to have any luck writing this all the way out, so I think I'm just going to leave it. Maybe I'll go a little bit farther. Just so let's kind of just skip this section, just to show you what to do when you get to this row. You would have, so we'll have dot dot dot. We'll have 4s, and then we will have, instead of 5 or 4d, we'll have 3d. And really, I won't ask you to know the different orientations. So for these, if you just had 2p for all of them, that'd be fine. And for this, if you just have 3d and then you have the right number of boxes there, that would also be fine. And basically, you would keep going through, so you'd have 4s, then 3d, then 4p, then 5s, then 4d, then 5p, and then you would just fill everything with electrons. You'd start out writing the up arrow, then down, up arrow, then down, up arrow, up arrow, up arrow, down arrow, down arrow, down arrow, and you would go through and do that for all of these. Ooh, I'm so glad didn't decide to go through and do it, because this is already going to be a lot of arrows. Okay, so this would be kind of the general approach, and then if you wanted to convert this from orbital notation to electron configuration notation, all you would do is you would turn this to this entire thing would become 1s2, 2s2, 2p6, whatever from these you just write it down. 4s2, 3d10, and you would just keep going. So that's all for our electron configuration notation. So let's see. I think I might make a third video. Actually, really close to being done. I guess there's only really two more things really to talk about. We have this notion of highest occupied level, which we've already kind of discussed. For example, in beryllium, the highest occupied level would be our 2s orbital. And it's basically just the highest level that an electron is in. And so, like I said, for beryllium and lithium, it would be the 2s orbital. For nitrogen, it would be the 2p orbital. So I think that's a pretty simple concept. I guess the only other thing to really think about is we kind of encountered the issue here with our xenon. That would be a lot of things to have to write down. So is there a faster way to write down the orientation? And as it turns out, there is. All we do is, let's see if I get rid of all of this. If I have something where, let me see if I can bring it back. So if I want to write out the, let's see, electron configuration for phosphorus, I could go through all of this, and all of that in that phosphorus, but I already kind of know what the orientation for neon is. That's a pretty standard value, and so I can use this thing called noble gas notation, where I just say it's got the same notation or the same configuration for neon, and then I just start tacking things on. So then I would have 3s2, because I would start here and then I'd go, this is 3, then I have 2 electrons that I can fit in those 2 locations, and then 1, 2, 3, so 3p3. So this is the equivalent way of writing out phosphorus's notation, or the electron configuration, just using noble gas notation. I think this is probably the way to go with a lot of these, because it can save you a lot of time just by writing. I guess the only other mentions that I have is know that these are your noble gases. They are the final row. We use them in our noble gas notation, and their big property is they have full s shells and full p shells. The s orbitals and p orbitals are full for whatever column or row they fall on. And the last thing, and I'm really not going to get too much into it. We have these lanthanides and actinides, and you know how with these D's we subtracted 1, so this would be 3D, this would be 4D, this would be 5 and 6D. For our lanthanides and actinides, instead of subtracting just 1, we would subtract 2. So we would go from barium, so this would be 6s2. Then we would hit our lanthanum, and we would subtract 2. So this would be, instead of 6, it would be 4. And so this would be 4f1. Hopefully that makes sense. I'm not going to stress the lanthanides and actinides, or however you pronounce them. I know I'm probably pronouncing them wrong. I'm not going to stress those too much. I think if you can write out the electron configuration for this part of the periodic table, I think you're good. So if you have any questions on that, please let me know sometime this week. With that being said, that's all I want to cover. So just let me know how you like this video, different ways I can improve, anything like that. thank you very much for watching through. See you tomorrow.